1.5 The Conditional and Biconditional Connectives. Now we introduce the conditional statement, which has the form if P, then Q, in which we call P the antecedent and we call Q the consequent. We also have a new logical connective, which is this arrow, that expresses if P, then Q. The logic behind the conditional statement is that if the assumptions are true, then the conclusion must also be true. The weird thing is when the assumptions are false, it doesn't matter whether the conclusions are true or false. The overall conditional statement will still be true. Think about it like this. We have this statement, if I go to the store, then I will buy some milk. Then you come home and turns out that you didn't go to the store. Your overall statement, which was the conditional, if I went to the store, I'll buy some milk, is still true because it's a hypothetical. Let's look at what happens with this logical connective in a truth table. So we have if P is true, then Q is true, then P to Q is true. If P is true and Q is false, we can't have that. So this will be false. Now, when we see that our assumptions part are false, it doesn't even matter whether Q is true or false. The overall statement will still be true. Now, let's look at the truth table for not P or Q. So I have all our possible options here, and first I'm going to negate P. So true becomes false, false, true, true. And now I'm going to compare that with not P or Q. So not P or Q, true, not P or Q is false, not P or Q is true, and that's also true. So now notice that if P then Q is the same in the truth tables as not P or Q. And if you notice before, when things have the same truth table, that means that they are equivalent. So that leads us to the conditional laws. Which state that if P, then Q is equivalent to not P or Q, which we just showed here with these two truth tables. And also, if P then Q is equivalent to the negation of P and not Q. The second one might not seem as obvious at first, but look at what happens when we apply De Morgan's law. Then we get this, and by double negation law, we have not P or Q. So again, notice how these turn out to actually be equivalent forms because of De Morgan's law and then the double negation law. Now we're going to look at a couple more related laws, which are the contrapositive law and the biconditional law. So the contrapositive law states that if P then Q is equivalent to not Q, then not P. So as our conditional law states above, if P then Q is equivalent to not P or Q. So now I'm going to try and see if I can turn this on the right side to a similar form on the left side. So not Q, if then not P. So if I'm going to write out this conditional connective here, then I have to negate what was the antecedent and then leave alone what the consequent was and then put an or between them. So I have to negate the antecedent put an or, and then leave the consequent alone. And by double negation law, this becomes Q or not P, which by commutative law is going to be the same thing as not P or Q. So again, we showed that these two are the same. And we also have our biconditional law. So biconditionals are going to have arrows in both directions. So not only do you have if P then Q, then you also have if Q then P. And that's also expressed as if and only if in the verbal form. So we have our law, P if and only if Q is equivalent to if P then Q and if Q then P. By contrapositive law, however, the biconditional of P and Q is also equivalent to if P then Q and not P then not Q. We can show that these two are the same thing when we just work them out. So if I have, see that later. Okay, so now we're going to work on problems. Analyze the logical form of the following. Mary will sell her house only if she can get a good price and find a nice apartment. So when they say analyze the logical form of the following, you kind of want to translate it into logical connectives and symbols and stuff like that. So you might think that this part will be the antecedent and these two parts are going to be the consequent. But actually that's not true because we want to look at this only if here. So we can also think of the statement reworded as if, only if Mary can get a good price and find a nice apartment, would then she sell her house. So it turns out like whatever is in front of this if is going to be our antecedent. And then what was on the left is our consequent. So it doesn't really matter the order that it's listed in, does it make logical sense? So I'm going to put this part, make this clause as symbolizing as P, and I'm going to put this part, I'm going to represent it as Q, and then I'm going to represent this part as R. So notice here this important piece and. So that's going to show us P and Q. If P and Q, then R. And that is our answer for this problem. Now this one is much trickier. 1.5.5 part A. Show that the biconditional P if and only if Q is equivalent to P and Q or not P and not Q. So first we want to break this biconditional down into our identities, which we had before of our biconditional law up here. So I'm going to use the first one. If P, then Q, and if Q, then P. I'm going to break this down using the conditional laws. So we have not P or Q and not Q or P. Now this part gets a little bit tricky. You might have not seen it before or expected it, but here it is. We're going to distribute these two parts on the left. So we're going to distribute the not P with the not Q or P, and we're also going to distribute the Q with the not Q or P. So I'm going to use brackets to kind of show which parts we're referring to. So we have not P and not Q or P. It's one part. Now we're going to have OR, and we're going to distribute the Q. Now we're going to distribute again these things on the inside. So we're going to have not P and not Q, or not P and P. Now for the right side, or Q and not Q, or Q and P. So notice these contradictions in the middle, and if you remember your contradiction equivalence law, these are going to cancel out, because when you have a contradiction with an OR of P, it's equivalent to P. So these just cancel out in the middle, and you're left with P and Q, or not P and not Q, which is exactly what we wanted. So we are done.